We have a 4-part series of video examples addressing the application of alkalinity concepts. These accompany Chapter 3 of the Handbook, Water Quality and Treatment, 6th edition. In this first of the 4-part series, we'll examine the calculation of the pH of pristine rainwater. Example 3.4 of Water Quality and Treatment, 6th edition does address the alkalinity of pristine rainwater. This video example expands upon the application of fundamental principles presented in Chapter 3. Hopefully, we can develop some improved understanding of the process for the chemical modeling of the pH of natural precipitation. And of course, this modeling process is applicable throughout many areas of environmental water chemistry. In the current context, pristine refers to rain that forms in the absence of air pollutants such as sulfur and nitrogen oxides. The actual character of pristine rainwater is ever-changing. So raindrops do form high in the clouds and fall to earth. They grow as they descend. Carbon dioxide is absorbed by the water in the droplet, and the associated chemical reactions occur quite rapidly. We generally assume that the droplet is at equilibrium with the surrounding atmosphere and that the acid-base reactions of water and the carbon dioxide system reach equilibrium conditions. Then, an impending impact with the earth. Within the raindrop, we have the following governing equilibrium. Carbon dioxide gas is at equilibrium with water in the atmosphere and the combination of carbon dioxide and carbonic acid dissolved in the aqueous solution. That carbonic acid species, carbon dioxide and carbonic acid, is at equilibrium with protons in the aqueous solution and bicarbonate. Bicarbonate is in turn at equilibrium with protons in the carbonate ion. Hydroxide and hydrogen ions are in equilibrium with water. Water and hydrogen ions are in equilibrium with the hydronium ion. We generally represent that equilibrium as the ion product of water. And of course, the chemical character of the raindrop will depend upon the quantity of carbon dioxide that has been absorbed during the descent. So we can write some equations for the chemical equilibria occurring within the raindrop. We have Henry's law, which relates the carbonic acid or dissolved carbon dioxide in the raindrop to the carbon dioxide in the atmosphere. We can express the partial pressure of carbon dioxide as the product of the total pressure and the concentration of carbon dioxide in the atmosphere. 10 to the minus sixth is the conversion from parts per million per volume to mole pressure or volume fraction. We have the equilibrium between bicarbonate and carbonic acid, the equilibrium between carbonate and bicarbonate, of course the equilibrium between hydroxide and hydronium or protons, the ion product of water. We can do a summation for the total inorganic carbon content of the water droplet as the carbonic acid or dissolved carbon dioxide plus bicarbonate plus carbonate. So at this point, we have 7 unknowns, but we have 6 equations. For our 7th equation, we account for the transfers of protons among the acid and base species within the water droplet. We know that every proton donated must be accepted. So we need a reference species for each acid system. We'll use water for the hydronium water hydroxide system. We'll use carbonic acid for the carbonic acid bicarbonate carbonate system. These are good choices because it is impossible to measure changes in the concentration of water within the droplet, and as governed by the air-water equilibrium, carbonic acid or dissolved carbon dioxide within the raindrop is invariant. So an increase in the proton or hydronium or hydrogen ion concentration is evidence of 1 proton per mole accepted by water. Increases in bicarbonate and carbonate are evidence of 1 and 2, respectively, protons per mole donated by carbonic acid. An increase in the hydroxide is evidence of 1 proton per mole donated by water. Now, the evidence of protons accepted must equal the evidence of protons donated. We wrote these all together into what we can call a proton balance, where the change in the hydrogen ion concentration has to equal the change in the bicarbonate plus twice the change in the carbonate plus the change in the hydroxide concentration. This delta is fleshed out by the final concentration of the species less the initial concentration of the species. Now we imagine the first molecule of water condensing on the seed particle in the cloud and realize that it must be pure liquid water. Therefore, the initial conditions of the solution are those of pure liquid water. Hydrogen ion, hydroxide ion concentrations are equal at approximately 10 to the minus 7th molar, depending upon the temperature. There is no bicarbonate, there is no carbonate present in that initial molecule of water. So since water and carbonic acid are the reference species, and they don't appear in the proton accounting equation or the proton balance, we do not need to know their initial concentrations. And the proton balance then reduces to the final hydrogen ion concentration has to equal the final bicarbonate concentration plus twice the final carbonate concentration plus the final hydroxide concentration. Now we have to be careful when we cancel the initial hydrogen ion and hydroxide concentrations that this operation on the left-hand side and the right-hand side of the proton balance can be done only when the initial pH condition of the water dictates that the initial hydrogen ion concentrations and hydroxide ion concentrations are equal, only for pure water. So we'd like to pare down the number of equations that we need to solve. Most conveniently, we can choose bicarbonate, the hydronium ion, and total carbonate as master unknowns and reduce the system to 3 equations in 3 unknowns. Normal total pressure varies from 1 atmosphere at sea level to about 7/10 of an atmosphere at an elevation of 3,050 meters. We can choose any value we wish located anywhere on the globe. We'll use an abundance of carbon dioxide in the atmosphere of 395.8 parts per million by volume. That'll yield the partial pressure of carbon dioxide, and of course from known partial pressure of carbon dioxide, we can calculate the carbonic acid concentration within the raindrop. Then we've written functions for bicarbonate as a function of carbonic acid, for carbonate as a function of bicarbonate, and for hydroxide as a function of the hydrogen ion concentration through the ion product of water. We substitute from these equilibrium expressions into the mole balance and into the proton balance. Then we'll drop the final subscript to make things a little simpler, as all of the terms in our resultant equations are final concentrations. Let's use MathCAD 15 for these computations. So we'll input our information. This symbol is an assignment statement used in MathCAD to put values into variables. We'll do the computation of our PCO2, employing our conversion from parts per million by volume to parts per part by volume, moles, or pressure. We'll compute our invariant concentration of carbon dioxide in the water droplet. So now we have 3 equations and 3 unknowns requiring a numerical method. In order to implement a numerical method, we of course need to give guesses for the 3 principal unknowns. We'll figure that the hydrogen ion concentration should be about 10 to the minus 6th molar, or pH about 6. Bicarbonate ought to be somewhere close to that value, and the total carbon ought to be something on the order of 10 to the minus 5th molar. In order to invoke MathCAD's solver, we use the statement given. Then, after the given statement, we simply express our 3 equations that we'd like to solve. This is the Boolean equal sign, which is like an algebraic equal sign used within MathCAD's solve blocks. Note that we've used that in all 3 equations. We finish up the solution of 3 equations and 3 unknowns with the find statement. And of course, within the argument of the find statement, we have to have our 3 unknowns. It's very convenient to take that find and the given along with it and assign it into a 3-row by 1-column matrix of H, HCO3, and total carbonate that we can use in later calculations. We see from this calculation that our calculated pH is 5.611. That very nicely compares with the value 5.6 used in example 3.4 of water quality and treatment. We finish up the computation by calculating the carbonate concentration and the hydroxide concentration. We see that those are very, very small. So let's see what the result would be if we neglected the carbonate ion concentration. We again have our MathCAD output. The only thing that we have done here is we've removed carbonate from the proton balance and the mass balance. We see here that our pHs to 4 significant figures identical to that for the full solution. You can also see what neglecting carbonate and hydroxide would do to the solution. And here again, after removing carbonate from the equations, we can remove hydroxide from the equations. And we see that our result is again to 4 significant figures identical with that of the full solution. Hydroxide and carbonate are very insignificant in this particular calculation. So let's perform this computation for the conditions at an elevation of 3,050 meters, about 10,000 feet. The only thing that we have to change is the total pressure of the atmosphere. Everything else is already programmed into the worksheet. Here we find that the pH of rain falling at a 10,000 foot elevation would be about 5.69, a little bit higher than at sea level, where the pressure would be 1 atmosphere. So results here support the pH of rain used in water quality and treatment, 6th edition example 3.4, but most importantly, our process illustrates the means to characterize pristine rain and certainly other varieties of water.